Good morning, and welcome to NET202. I'm Alan Halakmi. I'm a Senior Manager of Solutions Architecture at Amazon Web Services, and I help customers leverage the security and networking capabilities provided by AWS to deliver secure and performant systems. You're probably aware that the number of unallocated IPv4 addresses is almost complete. We're almost out of IPv4 addresses, but did you know that the exhaustion of the global IPv4 pool is expected next year? Did you know that IPv6 is growing at an exponential rate on the internet? In this session, I'm going to give you the basics about IPv6, and I'm going to show you how easy it is to leverage IPv6 on AWS. So an agenda. We'll review the pace of IPv6 adoption, key aspects of the protocol, and how to enable IPv6 across various AWS services. Now, this is an introductory course, so we're not going to learn IPv6 ninja moves on AWS, but this should give you the confidence that you will want to have as you start to go down a path of leveraging IPv6 in your applications. Let's start with the state of the IPv6 internet. This will be very brief, but just to give you a sense for the pace at which it is growing. So the data here we showed last year as well. I took this data at the end of October. Global IPv6 usage as seen from major websites was about 20%. I checked this morning, it's 22%. We expect to end the year just shy of 25%. At this time last year, the global usage was about 13%. We're seeing a lot of the movement coming from Europe and from parts of Asia. And it turns out that mobile and IoT are driving a lot of this demand. So here are the hotspots of usage, the top 5, if you will, by volume. And there's some dramatic movement in this list just from last year. So at this time last year, T-Mobile was showing 72% of their infrastructure using IPv6. Now they're up 17% to 89%. Another big mover was AT&T. Last year we saw that at 58%. 14% increase to 72%. So there's a lot of movement now, year over year, almost doubling in terms of IPv6 adoption. So now we'll talk about the protocol. Again, what I'd like you to come away from in this session is the basics and understanding of how it works at a kind of very fundamental level. We're not going to get into all the edge use cases and that type of thing, but hopefully this will give you the information that you need to feel comfortable using the protocol and having conversations about it. So I think most people know that IPv4 is a 32-bit address space. So that gives you about 4.3 billion addresses. I did you the courtesy of putting some binary up there. It's very exciting. This is the IPv6 address space, 128 bits. I think most people know that. It's about 29 orders of magnitude larger. So the bit space is 4 times as large, but in terms of the available address space, right, it's exponential, 29 orders of magnitude larger. And everybody has to put up their how big is IPv6 slide, so I'm putting one up too. So if you take a typical IPv4 subnet, a /24, you put a bunch of pixels on a 300 ppi screen and say each pixel is an IPv4 address, this is roughly how big your IPv4 screen would look. In IPv6, we go from inches to hundreds of miles, right? So this is a much larger address space. Okay. That requirement has now been checked. We talked about how big it is. Let's talk about address format. IPv4, dotted decimal notation, right? We have octets between each of them, so 8 bits represented by each of the 4. We use, these days, CIDR notation. /24 tells you the first 24 bits are fixed. So on the left side, I have, let's say, a routable address, a global unique address. And on the right side, I have a loopback address, right? Everybody knows loopback, 127.0.0.1. In IPv6, we use colon-separated hexstat format. Super easy to say. Colon-separated hexstat format. Duets are 2, quartets are 4, octets are 8, hextets are 16. So we have 16 bits represented in between each of the colons. If you take a look at the loopback address, you'll see that that's a super obnoxious address, right? That's a lot of zeros to put in. So we have 2 methods to reduce the size of the address in a way that's useful for humans. One is that we can take out any leading zeros, right? So step one, I've taken out leading zeros. That's great. Now, it's important to remember that you can only take out leading zeros. Otherwise, if you try to take out random zeros in each of the hextets, then the address becomes ambiguous. So only leading zeros can be removed. The next thing that we can do is a very specific notation, special syntax, if you will, double colon. So the double colon can represent any single contiguous string of hextets with a 0 value. So we'll be using this compressed format throughout the presentation. Another thing that most folks know about IPv6 is that we don't have broadcast addresses anymore. So in the IPv4 world, we think about the last address of a subnet. We think about the all ones address, all 255s at layer 3. And at layer 2, the all ones address, right? This is broadcast. We use this for things like ARP and for exchanging other types of data around the infrastructure when we need to get kind of broad view of the hosts on the infrastructure to get a response. In IPv6, we move to multicast. FF00/8 is the designated block for multicast addresses. And the one that you really should know is FF02::1. This is the all nodes multicast address. I put it up there, but I'm going to read it because I think it's actually interesting. Strictly speaking, in IPv4, this exists. 224.0.0.1 is the all nodes multicast address. But in practicality and reality, it's not used in IPv4. Instead, when we want to talk to all nodes, we send it out on the broadcast. In IPv6, this all nodes multicast address is functionally the same as an IPv4 broadcast address. In layer 2, because we're moving to multicast, there is a reserved range for IPv6 multicast, and it's the layer 2 addresses starting with 3333. IPv6 has a variety of unicast address types. Unicast addresses uniquely identify an interface of an IPv6 device, and they're used for one-to-one communication on the infrastructure. The first one that we'll cover is the unspecified address, the all zeros address. The unspecified address indicates the absence of an address. So why would that be useful? Well, the primary use case you'll probably see that for is something called duplicate address detection, or DAD. So let me give you the example. I have an infrastructure. Let's say this is a subnet. I have existing systems on that subnet, and I have a new instance or a new host or a new system that's coming up. It has an address that it wants to use, but it doesn't know whether it's in use yet. So how does it verify whether or not that address is usable? Well, it can send a packet out on the wire from a source address of all zeros, the unspecified address, to the destination of the address that it is tentatively planning to use. If it gets no response, it knows the address is available and it can use it. If it gets a response, then it knows that there's an address conflict and some resolution is required on its end to make sure that it doesn't come onto the network and overlap with another address. So the unspecified address is one of the unicast addresses for IPv6. The other one is loopback, right? This is the mechanism that's used to talk to oneself, if you will. It's how the system communicates to itself. We talked about this just a moment ago. It's 127.0.0.1 in IPv4. In IPv6, all zeros and 1. We'll show that in compressed format as well. All right, so far so good, right? This is fairly straightforward. The next set of addresses that we're going to talk about need to have some type of uniqueness associated with them. In IPv6, we call this the interface identifier. I have some information up here. I literally quoted RFCs, so if you like reading RFCs, you'll enjoy this. The interface identifier turns out to be a really important value, and how you derive it also turns out to be very important as well, both in terms of your ability to just get onto the network and make requests across the network for things like configuring yourself. It's also important because it has some significant security and privacy implications. So interface identifiers I'll talk about throughout because they're very important. IPv6 addresses in general consist of a prefix and an interface identifier. The interface identifier for unicast addresses is 64 bits. So I've got 64 bits of prefix, and I've got 64 bits of address identifier. Together, I have 128 bits that I uniquely identify an interface or a system that's on the IPv6 infrastructure. So let's talk about the first of these, link local addresses. Link local addresses have a scope of a link. That's the only scope in which they are usable. So if a router gets a link local address, it's not going to forward it anywhere. It's going to throw it away. Link local addresses are only usable on the local link. In the IPv4 world, it's the 169.254/16 block. You may know this IP address if you do much with EC2. This is the metadata service address. Interestingly, in IPv4, if you have this address on an interface, the RFCs say that when you get a routable address, RFC 19, right, a 10 dot or 192, or if you get a globally routable address, you should drop this, forget about it, and use the other address, right? So typically, the link local address is an ephemeral address. In IPv6, it's a required address. And in fact, every system will have this link local address. It may have other addresses as well, and we'll talk about that. The block for link local is FE80/10. And this is what a typical link local address will look like in IPv6. And I'll explain in a moment how I came to that address. So typical prefix is FE80/64. So although FE80/10 is the reserved block, there are obviously bits there that you could play with. The majority of implementations just use FE80/64 as the prefix portion of an address. Now we have the question, how do we get to the address, the interface identifier? There are a couple of approaches. We could do this manually. That turns out not to be a lot of fun. You can do this systematically using something called a modified EUI64 format, and we'll talk about that in a moment. You could also have this derived randomly. But because link local addresses are so important to the operation of IPv6, duplicate address detection using that unspecified address is almost always used. So let's talk about modified EUI64. So I have my link local address prefix, FE80/64. I have a MAC address on that NIC, right, my layer 2 MAC address. So then the question becomes, how do I go from a 48-bit MAC to a 64-bit interface identifier? It's a two-step process. Step 1, flip the 7th most significant bit. There's a long story as to why this is done. The most current RFCs say, essentially, don't worry about it, just do it. So here is our, I'm kind of expanding out the first set of bits here. There's our 7th most significant bit. We flipped that to a 0, and now instead of 02, we have 00. So there's my MAC address, still 48 bits. So somehow I need to add some additional bit magic in the middle. So what I'll do is I'll insert FFFE into the MAC address between the first 24 bits, which is the organizational unique identifier, and the last 24 bits, which is the device identifier. And now, with a little bit of bit stuffing, I have 64 bits as an interface identifier. So take my link local address prefix, take my interface identifier, and now I have my link local address. The next type of unicast address is a unique local address. I will hold my opinion on it, but it will be very clear just by the fact I'm saying I'm going to hold my opinion on it. In the IPv4 world, the way to think about this is RFC 1918, right? You're familiar with 10 dots, you're familiar with 192.168. The unique local address, the ULA, is conceptually similar, but it has a couple of differences that are material. One is that ULAs are designed to be globally unique, right? So today, I'm sure everybody's experienced the 10 dot overlap problem, double net, and all kinds of horrible things. The unique local address, which is also sometimes called the local IPv6 address, is designed to be globally unique, at least with a high degree of probability. It's in the FC00 /7 block. As a practical matter, it's FD00/8. The first bit currently is being reserved. This is what those addresses look like. The RFC that defines ULA describes a mechanism for calculating a pseudo-random value for what they call a global ID that you put into the part of the prefix. So there are 40 bits for this global ID. So the likelihood that you're going to have two organizations that connect to each other that use ULA and have an overlap is very slim. Keep in mind that 40 bits is 8 bits longer than the current bit allocation for IPv4, right? So a high degree of likelihood that there will not be overlap. So I'm not going to talk about how IP addresses are allocated for ULA. I'm not a fan. All right, global unicast addresses. This is how people talk to one another over the IPv6 internet. The way that this typically works in the world today is you have your IPv4 addresses, you go through a NAT, and you go to something on the internet. In the IPv6 world, in the majority of cases, certainly the desirable approach is that everybody has a globally unique address, right? Everybody uses these global unicast addresses, and they communicate end-to-end, no NAT. The IP address is obviously global, and the prefix is allocated by the regional internet registries. AWS has very large blocks, so we have 128-bit range. AWS has /23s and /22s that have been allocated. So we have very large address space available to share with you. So let's talk about address assignment for global unicast addresses. So we could do this manually. Again, comes a little bit of a hassle if you have any number of systems. You can do this in a systematic way using something called router advertisements. Router advertisements are a type of ICMP-v6 packet. And the router advertisement is sent to the all nodes multicast address. It has a flag called the managed address flag. And when that is set to 0, it tells the receiving instance or the receiving system that it should use something called stateless address autoconfiguration, SLAC. In that router advertisement, there's information about the prefix and the prefix length. There's information about the default gateway. And then the instance can use a mechanism, it might be modified UI64, to calculate its interface identifier, add that to the prefix, and it has established its IP address, its global unicast address. Now, modify UI64 is possible, and in fact, it was a popular way to address global unicast addresses, but it's fallen out of favor for a number of reasons that having to do with security and privacy. So imagine for a moment that you had an address that you were using on the internet that never changed. Moreover, because it was a modified UI64, it told some semantic information about you, like what kind of interface you're using. Is this a Cisco device that you're using this on? Is it a Juniper? Is it a Dell computer, right? That MAC address has some material in it that's actually quite useful. So for reasons that have to do with traffic correlation and location tracking and device-specific vulnerability targeting, it's fallen out of favor as the mechanism for configuring global unicast addresses. I've listed 2 RFCs if you're curious about the current recommended mode of addressing or the security and privacy implications of using something like modified UI64 for global unicast addresses. Those 2 RFCs will give you a lot of data. Now, if that router advertisement has that managed flag set to 1, then you're going to use DHCP. DHCP v6 I will not get into detail on here, but I will tell you that it is materially different from DHCP in v4. Has the same generic outcome, but the implementation is materially different. And of course, you could also go for random address assignment. And duplicate address detection is typically used, again, to make sure you're not stepping on a neighbor. All right, so we've talked about address assignments. Now, how do 2 nodes talk to one another, right? In v4, we know this, right? It's an IPv4 ARP. I check my local ARP cache. I send out an ARP request on the wire. Hey, this is my source L2 address. I send it out to the broadcast. I'm looking for 10.0.0.2. 10.0.0.2 replies. Here's my source address. 10.0.0.1, you can now reach me, right? Here's where to find me at layer 2. In IPv6, we use something called Neighbor Discovery Protocol. But before we talk about how that works, we need to go back to the issue of not having broadcast. IPv6 uses something called Solicited-Node Multicast. The point of Solicited-Node Multicast is to say, if I am, for example, trying to find out the L2 address, the layer 2 address, for an interface on the wire, why should I have everybody on the wire have to hear that announcement? How about instead, I target that announcement to specific interfaces that are likely to have the IPv6 address at layer 3 that I'm looking for. So we use something called Solicited-Node Multicast Address, and you'll see in a moment how that works. So Solicited-Node Multicast Address has a prefix, FF02:1 FF/104. If I have an IPv6 node address that I'm trying to find, let's say, using neighbor discovery, I'm going to send to that node's Solicited-Node Multicast Address. How do I derive that? Step 1, take the least significant 24 bits of the node address and add it to the Solicited-Node Multicast prefix. That is the Solicited-Node Multicast address for that IPv6 node. That also means that any other IPv6 node that ends in 00EC22 has the same Solicited-Node Multicast address. But that's still not the entire infrastructure. In fact, even in infrastructures that are pretty large, this is likely only to have 1 or 2 subscribers. At layer 2, what happens? Well, we said earlier that we have this 3333 prefix for multicast in IPv6. And I can use that for Solicited-Node Multicast at layer 2. So now I'm going to take the least significant 32 bits of that layer 3 Solicited-Node Multicast address, put it on the Ethernet prefix, and that is my layer 2 address. So this node subscribes to this layer 3 Solicited-Node Multicast address, and at layer 2, Ethernet will send it out to this address. All right, so putting it together, check your local neighbor cache. Send the neighbor solicitation, right? Where are you? Layer 2 source is EC21. The destination is the layer 2 Solicited-Node Multicast address. Layer 3 source is the EC21's address. Layer 3 destination is the layer 3 Solicited-Node Multicast address. The payload contains the IP address I'm actually looking for, since there are multiple people that could be subscribed to that same Solicited-Node Multicast address. Similarly, we have the neighbor advertisement back, providing the details about its layer 2 and layer 3 information. All right, so now there's a question, how do I get to IPv6 resources? And the answer to that totally depends on what your configuration is and what the configuration is of the entity on the other end of your request. In an IPv4 only world, we know this, right? Send a request to DNS, a record gets a response with an IP address, send my traffic. That's straightforward. If you want to enable IPv6, you can just add an IPv6 address to your server. This is a dual stack configuration. So here's my IPv4 address, my global unicast address for IPv6. And I'll just note here that we also have a link local address, because it's required. And if you take a look, you'll see that this is a modified EUI64 format. So that 08 becomes 0A when I flip that 7th bit. And you can see between the 27 and the ED, I added FFFE, right? So there's my link local address. So now I have a dual stack configuration. The end user is still only v4 enabled. So they go through their typical approach. But what happens when both sides are IPv6 enabled? They both have, for example, a dual stack configuration. Well, a DNS request is made. I feel obligated to note, if anybody knows DNS humor, this is as good as it gets, right? So an A record represents a 32-bit address, and a quad A record represents a 4 times 32, 128-bit address. So the DNS folks really had a jolly day coming up with that, I'm sure. So you have your quad A record for IPv6 addresses. And now the question is, which path is going to be taken? IPv6 or IPv4? The answer is, totally depends on the requester. They get the say. The reality is, these days, the typical default choice will be IPv6 to IPv6 when it's available. If you want more information, you should read RFC 3484, which goes into gruesome detail about recommended address selection processes. It's fantastic reading. Some other notable differences. So end-to-end, IPv6 is really about end-to-end connectivity using global unicast addresses. It's a big deal. It's part of the reason I'm not such a fan of ULA. So why do we have NAT? We have NAT because we ran out of IPv4 addresses. We were trying to conserve them, but it has a lot of cons, right? Address overlap conflicts, split horizon DNS, all kinds of trickery that we've done with applications. Think about like NAT traversal for IPsec, right? We've done all kinds of like unnatural things with protocols to work around NAT. So some things that you should know: just because you have a global unicast address does not mean that you've lost security. And it does not mean that you've lost your ability to protect your instances. Public address does not mean it is reachable. And in fact, we have several customers. I cover public sector customers. We have several public sector customers that have /8s in the IPv4 world, and they use them internally. They're not available on the internet, right? So public address doesn't mean it's necessarily reachable. Another important note, path MTU discovery is essentially required, so intermediary nodes are not allowed to fragment packets. The maximum payload of a single packet is way bigger. So we moved to about 4 gig for a maximum payload of an IPv6 packet. Much, much bigger. The way that we do that is using an extension header for jumbograms. So there is a main IPv6 header, and then you can chain on these extension headers to communicate hop-by-hop information or things, as I mentioned, like jumbograms. All right. So we've talked so far about the protocol. Hopefully you now have a pretty decent grasp of how it kind of operates. You feel comfortable with it. So I'm going to spend the rest of the time talking about IPv6 at AWS. So I'm going to cover what services are supported and what you need to do to enable them. The first service that was IPv6 enabled at AWS was the IoT service. Again, I mentioned earlier that the kind of exponential growth of IPv6 has really been driven by mobile and IoT. So December 2015, we started our IPv6 March. If you use the AWS IoT service, your data plane endpoint, right, this is where your IoT device communicates to, that has a v4 and a v6 address. You don't have to do anything. You have it. The control plane, how you communicate to our infrastructure to make changes in the AWS IoT service, that's IPv4 only today. Amazon S3 also supports IPv6, and there's nothing that you have to do other than add the word dual stack to your fully qualified domain name. So you can see here, in my case, halakmi.s3.dualstack. That's all you have to do, and you get an IPv6 address. Now I'm about to make a plug for one of our services on the next slide. So you'll see in purple, I've kind of outlined this file transfer is taking 32 seconds. Another service we have that supports IPv6 is S3 transfer acceleration. Also, nothing for you to do except add the word dual stack to your FQDN. So in this case, it's halakmi.s3-accelerated.dualstack. And you'll note, by the way, the transfer time on this one is about 8 seconds, if I recall. Yep, 8 seconds. CloudFront supports IPv6 as well. It's a checkbox in the distribution. If you've created a distribution after October of 2016, this is on by default, right? So a couple things to know about CloudFront and IPv6. First, if you're using URLs or signed cookies to restrict access to your content, and if you're using a custom policy that includes IP address as a parameter for restricting access, read our documentation before you enable IPv6. There are considerations that I'm not going to cover here that you should be aware of. But otherwise, it's a checkbox. There's a DNS resolution, no issues. This is, I'm actually using CloudFront here to connect to a web server that I've launched in EC2. EC2 is an origin for this CloudFront distribution. And all it's doing is providing back the client address and the exported for. So you can see I have an exported for address of, that's an IPv6 address. CloudFront uses IPv4 when it communicates to an origin. So your users can access CloudFront over IPv6. CloudFront will communicate to the origin over IPv4, which makes for a great transition story. We'll talk about how that's happened even at AWS in the recent weeks. API Gateway. API Gateway is now IPv6 enabled. A few weeks ago, API Gateway announced the ability to create what they call a regional endpoint. Before, API Gateway was only available through CloudFront, and they controlled the distribution. Now, if you create a regional endpoint, you can put your own custom CloudFront distribution in front of that origin, and you can enable IPv6. So it's now possible for you to use API Gateway with IPv6, creating a custom origin. AWS WAF supports IPv6. It has since launch. I've created a blacklist here, just to block an IP address. It's the one that I was using as I was putting the slides together. And as you would expect, it sees that IPv6 address, and the request is denied. So WAF supports IPv6 as well. Route 53 has supported quad A records, if you will, the returning of an IPv4 address for quite some time. But until about a year ago, Route 53 did not support queries over IPv6. So for about a year now, Route 53 has supported the ability to respond to queries over IPv6, and you can see a resolution there. And then last year at reInvent, we announced IPv6 for VPC. So I'm going to take a little bit to talk about what this is, how we've implemented, and some of the decisions we made and why. So we have a couple of tenets that we used when we started to work through how are we going to enable VPC. It's a very core technology for most of our customers. How are we going to IPv6 enable VPC? So the tenets are essentially deliver end-to-end connectivity, make it simple and secure. And so I want to call your attention to the last bullet here. Minimize assumptions about customer intent. This turns out to be really important from a security perspective. I mentioned to you earlier that generally, if IPv6 is available on both ends of a connection, it will be preferred. Because VPC is a dual stack infrastructure, you can imagine suddenly communications occurring in your infrastructure that you didn't anticipate because now two nodes have IPv6 addresses. So minimizing assumptions about customer intent was really important to the design. So a couple of decisions. First was, how are we going to deal with addresses? ULA, you know I'm a big fan. No, we don't support it. So we don't support network prefix translation. We don't support network address translation. It fails the end-to-end connectivity promise of IPv6. I mentioned earlier that privacy and security are not the same thing. But customers are really concerned about, I have a public IPv6 address, who can get to my node? While it's possible to protect your infrastructure with security groups, we introduced a concept called an egress-only internet gateway, and I'll talk about that in a bit. Global Unicast address, whose address? Well, it's our address. When you associate an IPv6 address to your VPC, we give you a fixed /56 IPv6 block. As you create subnets, those subnets are of a fixed /64 size. Given the first part of the presentation, it should be clear why. That's your prefix, and the interface identifier for your instances fills in the last 64 bits. Now, there are privacy extensions that are used in IPv6, also called temporary addresses, so that folks that are using the IPv6 internet, to avoid some of these concerns that I described earlier about being tracked and so on, they'll have a stable IPv6 address which can be used for incoming traffic, but they have a temporary or ephemeral IPv6 address that's used for traffic originating out, right? So you can imagine going to a website, and then every so often the address that you're using to connect to these websites is changing. But you have a stable address for things that are coming towards you. Let's say you're a server. Because the primary use case in VPC is customers that have instances where they want folks to come and consume, we don't support privacy addresses or temporary addresses because the use case really isn't quite material on AWS. If you have a use case that would benefit from it, I would love to hear about that afterwards. So addresses, global unicast, and obviously link local. Now there's a question about how we deal with assignment. I mentioned to you some of the considerations with the assignment. Well, you can do manual address configuration in AWS for IPv6. It's not recommended. Certainly if you're doing auto-scaling, it becomes a big problem. We also investigated whether we should use stateless address auto-configuration, SLAC. But it turns out that that actually doesn't work well in in VPC in the way that we think about delivering cloud services, right? We're API-driven. SLAC is host or instance-driven. So in order for us to maintain control of what instances do so that we can deliver packets, we use DHCP-v6. As an interesting side note, because AWS VPCs are always keeping track of the entire topology, it's actually a stateless DHCP implementation on our end, which is to say when a DHCP request is made, we don't actually have a DHCP server with a bunch of state on it. We look at the topology database and we return the information based on the state of the topology in the API calls that you've made. Security. This is a big one. IPv6, is it on by default? No. It's not on by default. We want to minimize our assumptions about customer intent. But even though we don't turn it on by default, your operating systems on EC2 are likely to launch dual stack these days, and they'll have a link local address on them. So to prevent, again, kind of accidental IPv6 traffic from passing around in your VPC, we will not allow the link local traffic to pass through the VPC until you've assigned a global unicast address to the interface. So if you go into VPC and you launch 2 instances, and even if you enable IPv6 on the subnet, if you haven't assigned them an IPv6 global unicast address, they won't be able to talk to each other over their link local addresses. So you must have a GUA. Route tables. It would be a really bad thing if we updated your route table with a v6 route that pointed to the internet, for example. So we don't do that. The thing we do is we create a local route, much like you have with IPv4, in the route tables that points to the CIDR block, the /56, that's allocated to your VPC. The story with security groups is it depends. So going back to the notion of intentionality, if you've used default security groups and a default network access control list, we will add the equivalent default configuration for IPv6. So as an example, the default network access control list in VPC permits traffic. There are no restrictions. If you haven't modified that and you enable IPv6 on your VPC, we will add an IPv6 rule in your NACL that permits IPv6 traffic. However, if you've modified your network access control list or your default security group, we will make no change because we will assume that you intended to restrict traffic. If you already have an IPv4 infrastructure on VPC today, moving to IPv6 is really simple. You associate a /56 with your VPC, you associate a /64 with your subnet, and you associate an IPv6 address with the ENI of the interface of your EC2 instance. Very simple. Now I want to go back and talk about this notion of having a global unicast address in the sense that a little bit of nervousness that I have a public address on my instance and can't everybody get to it. Well, I mentioned that in the IPv4 world, NAT is one of the things that we use to kind of control that, right? It's a one-way door. While it's possible to prevent inbound traffic with security groups in IPv6, we did introduce the egress-only internet gateway to provide a semantically similar way to think about traffic with IPv6. The egress-only internet gateway allows traffic that originates within your VPC to egress, but it doesn't allow traffic originating on the other side of the AIGW to come in, right? So in that way, it's semantically similar to NAT. So let's kind of put it all together. We have a region, we create a VPC, we have a v6 address. We create subnets, we give them addresses. We have edge gateways, EIGWs, VGWs. VGW, by the way, is Virtual Private Gateway. We configure route tables. So on the left side, you see a route table that says, I have a local route for my v6 CIDR block, and my default gateway, ::0, :/0, my default gateway is the internet. So that's what the subnet on the left does. For the subnet on the right, it says, well, there's this address that is available down my direct connect, so take my virtual private gateway, VGW ABC, to get to that network. And otherwise, the default route is through the egress-only internet gateway. You can launch resources in these subnets, give them IPv6 addresses. You can define a network access control list, put IPv6 restrictions on it, same with security groups. The other thing that I just want to call your attention to, we've kind of talked through it, but maybe it hasn't all kind of come together yet. What I'm not showing here is that while this instance has an IPv6 global unicast address, if it's running an EC2, it also has an IPv4 address. In addition to this IPv6 global unicast address, it also has a link local address. And for both of its unicast addresses, right, the link local and the global unicast, for both of those unicast addresses, it also subscribes to solicited-node multicast addresses. And it's also subscribed to the all hosts multicast address. So when you go into this instance and you say, hey, show me what you're listening on and what addresses you have, it may be a decent-sized list. We talked about connectivity with VGW, right, with the virtual private gateway. Direct Connect supports IPv6 for private virtual interfaces, right? This is essentially LAN-to-LAN connectivity using AWS Direct Connect, which is our private line service. You can also use Direct Connect public virtual interfaces with IPv6, which will give you access to our border network and the IPv6 resources that are available there, like S3 and API Gateway. We recently launched Direct Connect Gateway, which I won't get into a lot of detail here, but I will tell you that Direct Connect Gateway also supports IPv6. If you're curious what the customer end router would look like, here I have the two neighbors from the screenshots I just showed you. The first neighbor is a public virtual interface over IPv6. I can tell that because it has 556 prefixes that it's receiving from Amazon. The second neighbor is getting one prefix, and that's the private interface. It's receiving the prefix for that VPC. Of course, now that we have VPC, things that we launch in VPC can talk IPv6. So if you're using workspaces, you can talk native IPv6. So I've gone onto a workspace here. I've gone out to that web server that I'm hosting that's just returning back what addresses it sees coming in. You can see it's a native IPv6 response. AppStream 2.0, same story. Native v6 capable. We also support IPv6 on Application Load Balancer. So the Application Load Balancer, at the time that you create it, you have an option, if you're creating an internet ALB, you have an option to create a v4 or a dual stack ALB. If you create dual stack, you get an IPv6 address. Much like CloudFront, the Application Load Balancer will answer IPv6 addresses, but it passes them back as IPv4, which makes it great for transition. So you can communicate directly with an ALB. Here I've shown you just from a workstation going to that load balancer that's sitting in front of the web server I mentioned earlier. You see I get an X-forwarded 4, right? It's not a native connection all the way back to the EC2 instance. The client address, which I've grayed out, is the ENI interface ID, the ENI IPv4 address of the ALB in my VPC. And you can also have CloudFront in front of your ALB, right? Your ALB is an origin in CloudFront. And in that case, you get an interesting X-forwarded 4 because CloudFront talks IPv6. That's my client address. But then ALB gets an X-forwarded 4 that shows the IP address that CloudFront used to connect to the ALB. And the client address, again, is the ALB IP. So there's much more to come on the IPv6 front. We are not done by a long shot. But we rely on you, our customers, to help guide us where we should be prioritizing our work and what we should be delivering next. So fair enough. I will note if you're using VPN, if you are using an appliance, you can use IPv6 using a VPN appliance today. But that notwithstanding, I'm going to come off stage and take questions if you have them, but I welcome feedback on where we should be prioritizing our next set of features. And I wish you best of luck in implementing IPv6. Thank you.